Sorry for the delay. Okay. Yeah. I mean, so first, I mean, one thing to announce. Okay, the first project. I mean, as I have promised to you guys, I mean, has been uploaded on e-class. Okay, so please, go check it out if you have not, downloaded. And the one thing also to remind you guys is that the TA has also prepared a sign-up sheet for you to, as I told you, like you guys need to find a partner, okay, to form a team for the projects, for the small projects. Remember? So there's a sign-up sheet, okay, the TA has prepared for you to let us know, like, your team, who will be your team, okay? And I expect, okay, this team information collection will be done in 2 weeks, okay? Meaning by the end of next week. Okay, next week. Just want you guys to be aware. Okay, next week I will not be. There will be no class next week. You guys know that, right? I already told you guys I will be in Vienna for student recruitment. So that week, I mean, we will not have class. Okay, so but you guys are expected to tell us your team information before the end of next week. I think that's plenty of time for you to find your teammate, right? Okay. So next week is going to be what? End of next week. Let me check. Today is 22nd, right? End of next week. So it's going to be October, let's set it to be October 7th, Friday. Will it be okay? Friday, okay, before the next Friday, okay, October 7th, at least before the midnight, you guys need to let us know your team information because you guys need to work together for the project. Okay, and the first project has already announced. Okay, if you have not found your teammate before October 7th, okay, starting that weekend, the TA is going to randomly assign a teammate for you. Okay, and as I said, okay, it's not a good approach because. Well, some students never do anything for the project, So if you don't want to do everything by yourself, I mean, I suggest you find your teammate by yourself, okay? So last week, okay, we talked about linear regression, right? I show you 2 different ways to do that. Okay, one way takes n squared. Okay, n to the power of 2.6 to 2.4, n to the power of 2.4 to n to the power of 3. Okay, to get it done. Okay, it's called like. There's a closed form, okay, called the normal equation that given like a set of, a set of n data set, okay, a set of n data entries, okay. If you have n features, okay, then you can solve, inverse matrix. And to get this, get the optimal linear regression equation done, okay, I mean, with this time complexity. And the other approach, I mean, is to use a scikit-learn linear regression class, okay, which get your best result, okay, best linear regression, okay, in a time complexity n squared, which is better than the normal equation closed form. But as I said, okay, these two solutions they have like a they are dependent to the number of features, okay. Although like in our example, we only have like one feature, to be honest, okay. But in reality, okay, in many research problems, there are many features out there, okay. Just for one question, I mean, actually, like in the first homework, okay, I mean, if you observe it, you will see like there are several features, okay, which is actually common, okay, in many data science questions. So, okay, so when this solution, okay, has like a higher order of to a number of features, I mean, it's probably not good. It's an indication that they are not a good solution. Okay, so here we are trying to tell you another solution called the gradient descent. Okay, which actually the reason I introduced like linear regression is really like, you know, linear regression is actually a solution or like it's an algorithm in machine learning. Okay. And I told you I'm going to review some topic in machine learning which will be beneficial, I mean, for you to learn deep learning. But really, like teaching linear regression is really not the the reason for for that. Okay, the reason I want to bring up linear regression is because, okay, one method that compare with linear regression, this gradient descent, is the concept that you are going to see it appear so often in deep learning. Okay, so which is the reason I introduced linear regression. Okay, so what is gradient descent? Okay, it's a very generic optimization algorithm. Okay, which is used to find the optimal solution in a wide range of problems. Okay, the gradient descent is actually very simple. Okay, the general idea, okay, just to tweak parameters iteratively to find the the place that give you the minimal cost function. Okay, so for any optimization problem, you normally will have a cost function, okay, and you want to normally minimize that cost function. Okay, so if you try to visualize, okay, the cost function with like geometrically, okay, visualize it. I mean, try to visualize in a three-dimensional or like a two-dimensional situation. You have x1, x2, okay, and then the cost will be your third dimension, right? Okay, then it's going to be some kind of like a surface, right? It's going to be some kind of surface, and normally, I mean, when we say we want to find the place that give you the minimal value of the cost function, what we are really want to do, okay, is, okay, for that surface, we want to find the lowest, okay, the lowest place of the surface, okay, and so the idea is so simple, okay. So basically, okay, because it's once you consider that as a surface, okay, obviously, I mean, because like let me put it this way, okay? Most of the cost functions, they are continuous and they are differentiable, okay? Meaning they are smooth, right? They are smooth. So you can sort of imagine it as like a really just like some kind of like a curved surface, okay? So no matter where you go, okay, no matter where you are, okay, imagine you are a ball, okay? You are a ball, and you put yourself at any location, and because it's the surface has like a slope, right? Okay, because I mean, as I say, the curved surface has slope, right? So that slope will naturally bring that ball, okay, to the lowest position, right? Okay, it's kind of just like I mean, you just roll a ball on the ground, and the ball eventually will stop at the lowest place, right? Everybody know that, right? Well, it's a basic physics, right? Okay, so the gradient descent is doing exactly just like that. Exactly just like that, okay? So, okay, the gradient descent, first it measures local gradient of the error function, okay, with regards to the parameter vector theta. Okay, so this gradient actually tells us where to go to find a lower direction. Okay, the direction to go down, basically. Okay, that gradient this is a vector that just tell you which direction will go. You should that ball should go. Okay, to reach like a lower position. Okay, so it goes in the direction of descending gradient. Okay, descending. Okay, this is a key word. Okay, because as I said, we want to find the lowest place, okay, in the cost function. So once the gradient is 0, what do we mean by gradient is 0? Okay, remember gradient is basically the first order derivative. Okay, like just differentiate the cost function. I mean, you learn that from calculus, right? Like I'm not asking you to remember like all the detail of the calculus that you are learning. I'm just asking, okay, where you can find like the gradient, the first order derivative to become 0. It's a bottom of it's at the bottom, right? Okay, where like you are the gradient, the derivative is going to be 0, right? Or you can say, oh, I mean, it could be also on the top, right? Either at the top or at the bottom. Basically, it's extreme value. It's where the extreme value happens, right? Right? Any question with that? Okay. But here, okay, I want to emphasize that it's not very likely to be the maximal value. Okay, because we start, okay, remember, I say we place the ball at the random position, at the arbitrary position. So the situation where you happen to place the ball at a maximal location is unlikely, right? But when the ball, start moving, it must move downwards, right? It must move downwards. It doesn't move upwards, right? It is against physics, right? Okay, so I mean, eventually, okay, when the gradient reaches 0, okay, most likely you reach the minimum. Okay, it's impossible. I mean, when you roll the ball, okay, and when the ball stops, it stops at the highest place of the surface. It's against the physics, right? So that's the basic idea of gradient descent. Okay, so concretely, I mean, you start by feeding theta with random value. So as I said, this is called like a random initialization. So you start at any given location, okay, and then okay, you improve it gradually. Okay, when I say improve it gradually, okay, you are trying to find the direction that is going to reduce the cost function, okay, and you take baby step at a time, one baby step at a time. Okay, and each step is going to bring your cost function a little bit lower. Okay, and you keep doing that, okay, until the algorithm converge to a minimum. Okay, so this is like the basic idea of gradient descent. Very, very important, because the same idea is going to be used, okay, in deep learning again and again. Basically, like pretty much any model training, we are going to use gradient descent. Okay. So there's an important parameter in gradient descent. Okay, it's the size of the step. Okay. Okay. It is determined. Actually, the size of each step is determined by two things, not by one. Okay. The first one is the slope. Okay. How steep the slope is. You can imagine. Okay. The steeper the slope, okay, the bigger the vector. Okay, the bigger the vector. Okay. And second is like this learning rate. This learning rate, okay, will be used to multiply with the vector that you obtain. Okay, to tell you, I mean, you know, for each iteration, you know, where you are to end up, you are going to end up with. Okay, from the previous position. Okay. So this learning rate is very important. Okay, as I will show you in several examples that, okay, if the learning rate is too high, okay, the result may not be, you know, it may not converge. Okay, you may get a jumpy result. Okay, why is that? I will show you with the example. Okay, but if the learning rate is too small, okay, you can imagine. Okay, you are trying to get to the minimum. Okay, but each time you are going to take a very small step. Okay, so eventually it's going to take too much time. Okay, you are going to go through many iterations. Okay, in order to reach the minimum. Okay, so that's either situation, I mean, will not be good. Okay, so we will have to find a good learning rate value. Okay, I will tell you like how we can find a good learning rate value. Okay, later. Okay, so not all cost function look like a nice regular ball. Okay, if it's a very simple regular ball, then as you can imagine, like the ball must roll to the bottom of the ball, right? So that's like very simple. Okay, but unfortunately, okay, some cost functions, okay, may look very ugly. Okay, so there may be holes. Okay, holes means there are some discontinued locations. Okay, but this situation does not happen very often. I just want you to be aware. Okay, and the ridges, plateaus. Okay, I hope you guys, have no problem with these English words. Okay, basically like you just describe all sorts of irregular terrains. Just describe different shape of terrain. Okay, so this will make the convergence, okay, to minimum, okay, difficult. Okay, so exactly, what difficulty are we going to face? There are two, situations that we don't want to see. Okay, the first one is, okay, yeah, it converge. Okay, when you roll a ball, okay, it may stop, but unfortunately, it may stop at the local minimum, right? When you reach a local minimum, obviously, the first order derivative is also zero, right? But obviously, a local minimum is not, as good as the global minimum, okay? Because normally, when you want to find the optimized solution, okay, you want to find the global optimum, not the local global minimum, not local minimum, okay? So if this happens, obviously it's not the ideal situation. So we are going to also discuss what you can do to get to, what should I say, to avoid this. To be honest, this problem cannot be completely avoided. Okay, you can only mitigate it. Okay, reduce the chance this happen. This is going to happen, but it may happen. Okay, it may happen. Okay, the second one is it may take a long time to close the plateau. Okay, I mean if you happen to, that the converge will has to go through like a long plateau before it reach the the minimum, before it reach the minimum. So that that plateau, okay, plateau basically 高原啊, okay, 高原. So I mean in a plateau, okay, basically the height are similar. Maybe it has a little bit slope, but the slope is very small. Okay, so because the slope is small, remember I told you there are two things that control the movement of this ball, right? The first one is turning rate. The second one is the gradient, right? Okay, the gradient. Because in the situation of the plateau, okay, the gradient is also very small, okay, because it has similar height, okay. So it will take a long time for you to travel, okay, through the plateau to reach the minimum, okay, and a lot of time because after all this is an iterative approach, right? So sometimes you will set like a upper bound for this number of iteration. So when the program reach this upper bound, and unfortunately the ball is still in the plateau, so you haven't reached the minimum, right? So this could happen, okay. So I'm also going to discuss how you can try to avoid it, okay. So if I use a two-dimensional, okay, because on slides I can only show you two-dimensional situation. Of course, in your mind, I really suggest you to think of it as three-dimensional cases, okay. But for two-dimensional situation, okay, it's kind of you have curve. This direction is just your feature. This is your cost function value, okay. X is your feature, Y is your cost function. So if you have one feature, okay, and you can start at any random location, and you, as I say, you determine which direction, okay, will give you a smaller cost function. So in this two-dimensional situation, because it's basically it's a curve. So it's just one first order derivative will tell you, okay, if you travel to this direction, okay, when you increase the value of theta, if you are here, it will tell you if you increase the value of theta, it's going to give you a smaller cost function, okay. And based on this idea as well as the slope you are getting, the slope is the gradient, right, as I said, okay, then you multiply the slope with your learning rate, and then you update your theta position from here to here, okay. This is the update, okay, and you can keep doing that. But you can see that, okay, actually the moving, the movement, okay, the moving update is becoming smaller and smaller. right? This reduction of the update is not caused by the learning rate. As I said, the learning rate, okay, normally, okay, at least like at the current, I mean, at the current moment, we are assuming the learning rate is fixed, okay. The reason this updated interval becoming smaller and smaller, it's because the slope becomes smaller and smaller, right? Okay, as it approaches this place. So eventually, okay, when it gets to very close to the optimal solution, you can see the curve, the slope, okay, of the tangent, which is the derivative of I mean you get for the first order derivative. I mean it's close to zero. Okay, so this update becomes smaller and smaller. Okay, so this is like a visualization of gradient descent. Okay, when the learning rate is ideal. Okay, the learning rate is set ideal. Okay, why do I say that? Okay, this is a situation when you set the learning rate too small. I mean, it is still going to, go to the minimum, but you can see that it's going to take a much more number of iterations than this one, right? Obviously. Okay, so if you set the learning rate too small, I mean, you may have this problem. Okay, it's going to take many iterations to reach the minimum. Okay, and how about if you set the learning rate too large? Okay, assuming we are here. Okay, and you set the learning rate large, what happens is that, okay, at this place, because it tells you, well, in order to get a smaller cost function value, you should go to the, you should increase the theta value. And then that derivative, that slope, okay, will be multiplied by the learning rate. And unfortunately, in this situation, the learning rate is too big. So it goes directly to here. So at this place, okay, well, the first order derivative will tell you, okay, in order to get the smaller cost function, you should go to, you should reduce the theta value. Okay, so the slope will point to this direction. Okay, but again, because the learning rate is big, so instead of just moving a little bit closer to this place, okay, you go all the way to here, and this range is going to be bigger. Why? Because the slope at this point is bigger than the slope at this point, right? If you have a fixed learning rate, assuming that learning rate is big, okay, then the update is going to become bigger and bigger and bigger and bigger. Okay, so this is a situation when the learning rate is too large. Okay, so you also want to avoid that situation. And this is the visualization for the difficulty that I mentioned, those two difficulties that I mentioned for the gradient descent. The first one is local minimum. You can see this is a global minimum. This is local minimum. But when you roll the ball, okay, you may end up at local minimum because you don't know where you start the optimization, right? It could be any random location. So if you happen to start from the local minimum, from somewhere close to local minimum, you may, converge to a local minimum. That's the first problem I mentioned for the gradient descent. Okay. The second situation is this plateau. Okay. I mean, the converge may have to go through a long plateau, which, well, it may have a little bit slope, but the slope is really not that big. So because the slope is small, so you have to, go through this plateau like with many iterations. So, well, so it takes a long time to reach the global minimum. Okay, so these two difficulties. I mean, if you use a figure to show it, I think this is one of the visualized example. Okay. So, as I said, like of course, like these difficulties, okay, or like those like local minimum, global minimum, or plateau, okay, all these situations, okay, even with like remember I told you that your cost function may not be continuous, okay, or may not be differentiable. I mean, but as I said, the situation for that is not very often. But okay, remember, okay, in the case of the linear regression that we discussed, okay, what is the cost function? We assume we are using mean square MSE, right? Okay, the mean square error, okay, is our cost function, okay, for the linear regression model, okay. So mean square error is basically like your estimated y, okay, minus the true value, right? True value y square, okay, and you sum up all these things and divide it by the number of samples, which is m, okay? So because it's a simple, well, quadratic function, so it is a convex. It's a convex function, okay? We can prove that very easily. It's a convex function. What do we mean by convex function? Okay, geometrically speaking, if something is convex, it means that if you pick any 2 points on the surface and you draw a straight line, okay, between these 2 points, okay, that point, that segment, okay, the segment, okay, connecting those 2 points will never cross the curve, will never cross your convex function again. There will be no solution in the convex function. So based on this idea, okay, it actually implies that there are no local minima, just one global minimum. Okay, if you basically for a convex function, no matter how you draw it, it's going to look like something just like a ball, okay. So it is also continuous function with a slope that never changes abruptly, okay, because it's a quadratic form, right? And we can differentiate at any location, which is good, okay? So it's continuous, and the slope never changes abruptly. So MSE is a good cost function. I'm not saying all the cost functions look like that, but I'm saying now, because we are dealing with linear regression situation, so MSE, the cost function happen to be MSE, and MSE has all these good properties, okay? So, well, so at the end, okay, it tells you that, okay, gradient descent is guaranteed to approach arbitrarily close to the global minimum for the linear regression situation, okay? If you wait long enough, and if the learning rate is not too high, okay, as long as you have these two assumptions, okay, and we know the cost function has a shape of a ball, okay, for MSE, yes, it's going to look like a shape of a ball, but it can be an elongated ball if the features have very different scales. Okay, what do we mean? What is the elongated ball? Okay, I'm a big fan of college football, but you guys probably don't know what the football is. when you guys mention football, you probably consider football as a soccer, right? 就是大学美式足球。Have you guys watched those games, or you guys at least heard of rugby, right? 橄榄球 rugby. Okay, so the ball played in rugby or college football, it looks like this shape, right? It's not round, right? It's a little bit, it looks like, that's, if you get that ball and then you try to cut it in half, okay, the shape you are getting, okay, is what we meant by elongated ball. Or if I show you a figure, it looks like this. Okay, this is the lowest place. Okay, but you can see it's here we have like we are actually trying to visualize a three-dimensional situation. Okay, so we have theta 1, theta 2. Okay, we have two features. Okay, two parameters, and the height is indicated by the color. The lighter the color, the lower. Okay, the lighter the color, the lower. So these two figures actually shows. They show like a three-dimensional situation. But unfortunately, because we have slides only. Okay, the slide can only show this three-dimensional in two-dimensional case. But we use color to show you. Okay, so this looks like a ball, right? Okay, it's just like a ball that you use to eat your rice, right? Okay, so this is like a lowest place. Okay, but the elongated ball is like this. Here we have the lowest place, or like an optimal location, but well, it's not like a round shape. It's like this shape. It looks elliptic. Okay, elliptic. Okay, that's what I meant by like if you have a ball from rugby. Okay, you cut it like in this direction, then what happens is you are going to get something like this. So this happens when you have two different, the scales of your features are very different. Okay, if the scale of theta 1 and theta 2 are very different. Okay, so okay, when you using gradient descent, okay, you should try to avoid that elongated ball situation. Okay, you should ensure that all features have similar scale. Okay, how do we do that? You can use the scikit-learn. There's a standard scalar class. Okay, we are going to talk about these things later. Okay, but anyway, like just want to give you a head up. Okay, so this standard scalar class is going to normalize different features, okay, and help you to avoid elongated ball situation. But obviously, let me tell you, okay, sometimes you cannot completely avoid that. But so you may ask, so what is like why do we not want elongated ball situation? Okay, you can see like well, in the regular ball situation, okay, it converges directly toward the minimum. Okay, in the elongated ball, okay, if you have tried to, well, probably you don't have this experience, but you can imagine elongated ball, okay, and if you place a ball somewhere like here, okay, you will see that because this direction, this y direction, okay, at the y direction, like you are going to get the larger gradient, right? Because it goes down faster. And at x, x direction, the gradient is smaller. Okay, the gradient is smaller. The y gradient, the gradient for y is larger. The gradient for x is smaller. So what happens is that, okay, it's going to go this route. Okay, at the beginning, because you have a larger y gradient, so it actually goes down faster. And then gradually, okay, when it goes to here, I mean, it gradually like, turn and then reach the minimum. So what happened is that, okay, there are two things I would like to say. First, which distance, okay, assuming you start from similar location, it's difficult to say like because it's a randomized location, but assuming you start from a similar location, okay, which distance is smaller? The left-hand side, right? Why? Because it's a straight line, right? We know straight line beats the curve, right? Okay, in terms of this, I mean, reaching a location. Okay, if you want to go there, going straight, obviously, is faster than going, detour, right? So this one, okay, because the distance is shorter, so it will converge faster, right? Okay. Second, okay, when you go this route, okay, it doesn't go in the direction of the minimum. So sometimes you can see like even like a fluctuation, like here. So it goes like actually like this, not exactly this good. Okay, like this curve. It goes actually like this. Okay, so it's going to even further increase the distance. Okay, so that's why the elongated ball, okay, is not as ideal as like a regular ball. Okay, so we would like to. That's why we want to normalize, okay, each feature to make them like at the same scale. Okay, so well. So let's take a 10 minutes break. When we come back, we will continue the discussion of the gradient descent. Okay?